About 200 years ago, the Earth looked very different. The continents were once joined together, forming a supercontinent called Pangaea.
But how did they separate and form the world we know today?
Meet Alfred Wegener, a German meteorologist and geophysicist who formulated the first complete statement of the continental drift hypothesis. Wegener believed that all continents were once connected and have drifted apart over time. This idea, known as continental drift, was proposed in the early 20th century.
But not everyone was convinced. Scientists rejected Alfred Wegener's idea of continental drift because he could not provide a satisfactory explanation for the force that would drive the continents to move. His theory was also contrary to the prevailing belief that the Earth's crust was solid and immovable.
However, Wegener had some compelling evidence to support his theory. One of the first pieces of evidence was the matching coastlines or fitting of continents like South America and Africa. They seemed to fit like puzzle pieces.
Another evidence was the discovery of fossil evidence of plants and animals on continents that are now separated by vast oceans.
Geological formations or similar rock formations and mountain ranges were also found on continents that are now far apart.
Lastly, the glacial evidence. Wegener learned that there was evidence showing that the presence of a glacial period dated about 300 million years ago in South Africa, South America, Australia, and India.
But the real breakthrough came in the mid-20th century with the discovery of the theory of plate tectonics.
A more comprehensive explanation of the movement of continent and ocean floor, known as the theory of plate tectonics, states that the lithosphere includes the uppermost mantle and the overlying crust, behaves as a strong, rigid layer which is broken into segments known as plates.
This theory states that the Earth's crust is made out of plates and they move and interact with each other in three main ways. Divergent boundaries, where plates move apart, creating new ocean floors, and volcanic activity. Convergent boundaries, where plates collide, resulting in mountain formations, earthquakes, and volcanic activity. And transform boundaries, where plates slide past each other, causing earthquakes. Moving on to the evidence supporting the plate tectonic theory.
We first have ocean drilling as a supportive evidence. The Deep Sea Drilling Project was used to collect data from the seafloor to establish its age. The data showed that the ocean floor increases in age as it moves farther away from the ridge crest, which supports the seafloor spreading hypothesis.
But that's not all. Hotspots, like the one responsible for the formation of Hawaiian Islands, have also provided evidence for plate movements. By using a radiometric dating of Hawaiian Island Emperor seamount chains, provide that volcanoes increase in age as they move away from the hotspot. This is another key piece of evidence that supports the plate tectonic theory. But how do we know which directions the plates are moving in? That's where paleomagnetism comes in.
Paleomagnetism is the study of magnetism of ancient rocks. Several paleomagnetic data were collected in rocks to determine the direction of the magnetic poles at a specific time. Apparent polar wandering, by analyzing multiple data from paleomagnetism of rocks in Europe and North America, showed that there was an apparent change in the position of magnetic poles over time. This is another crucial piece of evidence for the plate tectonic theory.
But what causes the movement of these plates? It all comes down to convection currents within the Earth's mantle. Hot, less dense materials rises, while cooler, denser material sinks, creating a circular flow that drags the plates along. There are two proposed models for this movement.
The first is the layer cake, convection model. Some researchers propose that the mantle is divided into two zones of convection, which is a thin layer in the upper mantle and a thick layer located below. This model is known as the layer cake model. The other one is the whole mantle convection model. Other researchers support the whole mantle convection where denser oceanic lithosphere sinks and may even reach the core mantle boundary. But it's not just convection that drives the movement of plates. There are gravity-driven mechanisms at play as well, known as slab pull and ridge push.
Slab pull and ridge push are mechanisms aside from this heat-driven in the movements of plates. These mechanisms, along with convections, work together to the shape of Earth's surface and give us diverse landscapes that we see today.
Today, the theory of plate tectonics has helped us understand the dynamic forces that shape our planet and continue to shape it as we speak. So the next time you look at a map, remember that the continents were once one big landmass and that they're still moving today, thanks to Alfred Wegener's groundbreaking theory of continental drift.
And that's all for today. Thank you for watching.